Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so it's with a lot of pleasure that we have two visitors from the University of Illinois. They're both being funded under the Intel Microsoft University Computer Center project, UPCRC, Robert Burchino and Vikram Advi. And Robert will be giving the talk today on Deterministic Parallel Java. And Robert is a graduate student in the computer science department, I guess, at the University of Illinois, interested in parallel languages and compilers, and particularly in looking at safety and performance of parallel languages. And he has a BA in mathematics from University of Harvard University. And most interesting, he actually has a law degree from Harvard, too, and decided to abandon the law and come over to the dark side in engineering. So I'll let Robert take over.
Thanks very much. Good morning, everyone. I'm Robert Burchino, and I'm going to present some work today that I've been doing at Illinois with Vikram, my advisor, and several other people. And the title of the talk is Deterministic Parallel Java Towards Deterministic-by-Default Parallel Programming. All right, so I'd like to begin with a very short introduction on the concept of determinism. So the idea of determinism in computer programming is that the same input is always going to produce the same output. And particularly when you're doing compute-intensive work, a lot of algorithms actually have this property or mostly have this property, maybe with a few exceptions. And so what we're talking about here is going to be a non-interactive computation. That means you're giving it some input, it's computing, it's producing some output. Also, it's characteristic of this type of application that the parallelism is going to be for performance. So it's not part of the algorithm specification, but you want things to go faster on multiple cores. So some examples include scientific programming, games, voice, video, AI, et cetera, et cetera. There are lots of examples like this. Languages can also be deterministic. So by deterministic language, I mean that if you take a program and you pass it through the compiler and everything checks, then the program that you get has this determinism property. And examples include purely functional languages, so something like parallel Haskell. Also, there are SIMD models that are deterministic, so Fortran 9095, CUDA for the NVIDIA GPU would be an example of this. There's also some explicit data flow languages, so Sisal is an example. Also, Intel has this thing called concurrent collections that they're working on that's kind of a data flow model. Okay, so I contend that deterministic languages are really important for several reasons. So one reason is that if you have a deterministic language and therefore your programs are all deterministic, then you can reason about them almost sequentially, even though they execute in parallel. Determinism eliminates a lot of subtle parallelism bugs. You can avoid all sorts of complexities like data races, deadlocks, complicated memory models that can kind of make your head hurt. It's also very simple to test deterministic programs because there's only one output to check per input. So the problem, we hope, is about as easy or difficult as it would be for regular sequential testing. And also, hopefully it's going to be easier to port sequential to parallel code because you might still have to make some changes to expose parallelism, but hopefully the ported program is going to look an awful lot like the original sequential program. So if you've thoroughly tested your original sequential program, you hopefully have a high degree of confidence that the ported program is correct. And it's also simpler to reproduce bugs and do debugging, again, because you can mostly think about it in a familiar sequential way. So the overall point here is that if you can guarantee determinism for parallel programs, then parallel program becomes simpler. Okay. Unfortunately, it's not so easy to do that. And in particular, it's not so easy in the case that you're updating shared memory. So if you have a program, say like an object-oriented programming, where you're passing pointers to mutable state around and you have multiple threads going and they're reading and writing, then it's hard to provide static guarantees of determinism because it's hard for the compiler to know what's going on. It's also possible to add runtime checks that can rectify this problem, but runtime checks have their own problems. You either have to do them in software or hardware, If you do them in software, you're going to add extra overhead because you have to check all these reads and writes. If you're going to do them in hardware, the extra hardware you need might be complicated, might not be available on all platforms. And also, I contend that if you're only relying on runtime checks to get this determinism guarantee, then you will get the correctness, but the performance analysis and tuning are going to become harder because you might be, if you're speculating or if you're checking things and you don't know whether the program is going to run or whether it's going to fail, that just makes things harder, right? So you'd like to do as much statically as you can, although some things may not be possible statically. So for these reasons, I contend that the widely used languages today generally don't guarantee determinism. So if you think about something like C, Java, C#, things like that, generally there's no guarantee. And it's just up to the programmer to make sure if they want the determinism that they have to do it themselves and make sure it's correct and test it. OK, so this leads to the project that we're working on at U of I. It's called Deterministic Parallel Java, or DPJ. So I've put up the sort of main bullet points here of what the project's about. So the first point is we want to try to introduce determinism into a modern object-oriented language. So we chose Java for this exercise. We could just as easily have chosen something like C# or C++ or any other object-oriented language. We think Java is a good choice. So the idea is to have the compiler guarantee determinism by default. So it's an explicitly parallel language, but we want it to be deterministic, and we want the compiler to guarantee that. And as I said before, the goal here is to use static type checking as much as we can. So part of this research exercise is to sort of see, OK, what can we do with static types and what can't we do? And so we kind of want to really push the boundaries on the static type checking. But then when we see that that's not working well or that it might be a little impractical, then we also want to be able to fall back on runtime checks as the sort of second line of defense. We also think it's important to allow limited nondeterminism, and I'll talk about this more a little later, but the way we see it is there's basically two kinds of nondeterminism. So one is where you have nondeterminism going on in some part of the program that might be encapsulated in a library or a framework, and maybe the programmer doesn't really have to worry about that. So from the programmer's point of view, it just sort of looks like a deterministic computation kind of at the interface level, but there's some fine-grained locking or something going on inside. And then the second kind is where the programmer actually needs to think about the nondeterminism because it's in order to get more parallelism, you need to allow that kind of at the client level. And an example of that would be like atomic transactions, right? Okay, so here I've put the broad research goals of the project, and then once I've stated these, then I'll go through them in order and sort of talk about what we're doing for them. So the first research goal is how to guarantee determinism by default using a combination of static and runtime checks. The second research goal is if we have this local nondeterminism, how do we encapsulate that and make sure that the rest of the program is safe and deterministic, assuming that there's some sort of guarantee provided by the encapsulated piece. And then the third point is how to specify explicit nondeterminism when that's what you want, and how to make the nondeterminism and the determinism interact in a way that you can reason about. And then the fourth point is more of a usability point. It's how to simplify porting to a deterministic language, and that also includes just writing programs in a deterministic language. So you want to make it easier to write annotations, reason about the parallelism and so forth, and we think that compilers and development tools can really help with that. All right, so now on the first point of guaranteeing determinism. So our fundamental approach here, oh, and by the way, I think we have plenty of time for this talk, so if you have questions at any time, just go ahead. And, go ahead.
So
sure.
What kind of parallelism are you targeting? Do you think of data parallel programs or arbitrary?
Could be both, yeah. So
arbitrary for join parallelisms.
Right. Yeah, so a little later I'll get to some examples, and it should make clearer sort of. So we haven't yet, studied the full range of parallel programs. We've sort of focused on certain subsets, but the goal here is to make it very general and to support just general parallelism. Yeah. But obviously, the more unstructured it gets, the harder it is to do things with the static type checking. So that's kind of where we are. Okay, so yeah.
Do you see compiling down to a DAG and then scheduling the nodes of those DAG in order to get parallel
That's currently not the way we do it. You could do that. The way we do it now is we compile to the fork join task library in Java. So we basically, have a source-to-source transform, and then we just have something that basically has library calls that spawns the tasks. But yeah, you could compile down to an explicit DAG, and then that might allow you to do some analysis optimization on the DAG, but we don't currently do that. Okay, so the idea here is we want to have an explicit type and effect system where we define what we call our regions, and then we use those regions to partition the heap. So that kind of gives a way to specify what's what in the heap space. And then you can use the regions to annotate methods with effect summaries that say what pieces of the heap are being read and written. And then once you've done all that, then the compiler can check that the method summaries are correct, and also that parallel code sections are correctly synchronized. So there's no read-write interference going on that's going to violate determinism guarantee. And we also have some runtime support. So the main kinds of runtime support we need are, first of all, to do fine-grained synchronization, like producer-consumer synchronization. We just need some runtime synchronization construct to support that. And I'll talk a little bit about what we have for that so far. And also, in some cases, if we can't provide a static guarantee, then we need some kind of runtime support that's just going to do a check and check for certain sanity conditions. And if those conditions aren't met at runtime, then it would just stop with it, either produce a warning or stop executing. Okay, so now I have a very simple example of regions and effects just to kind of get your head around how they work. So this is a very simple sort of toy example, but it illustrates some of the basic concepts. So what I want to do here is I've got a class, C, that I've defined, and it's got two fields, F1 and F2, and I want to declare two regions. So these are names R1 and R2 that I can use in this very simple example to just partition C objects into two pieces, and I've coded them, red and blue. So R1 is blue and R2 is red. And then pictorially, it's illustrated over here that on the heap at runtime, I might have something that looks like this, right? Okay, so that's how I partition the heap. Basically, I declare these region names, and then I can put the fields in the regions. Okay. Then once I've done that, I can use the region names to summarize the method effects. So I've got a method M1 that is assigning to F1, so its effect summary is writes R1, and similarly, I've got a method M2 that's writing to field 2, so its summary is writes R2. And then once I've done that, I can have another method that invokes those first two methods in parallel with a cobegin. So this just says, do the two statements in parallel. And then the compiler can use the effect summaries to infer that the effect of this method is to write R1, and the effect of this method is to write R2. And R1 and R2 are distinct names, so in this case, it can prove that there's no interference and everything's good. So this is kind of the very simplest example of how you would use effects. And then in a little bit, I'll get into some more complicated examples that come up in real codes. Okay, so then I'd like to talk about some of the interesting parallel patterns that we can do. So you can use effects to do a number of things. And I'm not going to talk about all of them here today because some of them are pretty simple. Some of them are known. So they're very, very useful ones that are sort of very straightforward. But I'm going to talk about the ones that sort of new or interesting that we developed as we've been doing this work. So here are 4 of them. So one of them is a parallel update. So you've got an array of disjoint objects, and you want to run over the array and update all the objects in parallel, going through the references. And what's hard about that is you're following references, right? So you want to do that. The second one is to distinguish disjoint parts of nested shapes. So if you have, say, like a tree, and there's some notion of a left subtree and a right subtree kind of under the root, and then you want to traverse that tree in parallel and update it, how can you prove that actually it is a tree, and because of the data structure and the traversal pattern, the update is safe? Okay. Another example is a divide and conquer operation on an array. So that's similar to the tree data structure example, except that you're taking an array and chopping it into pieces. So you're basically making an array into a tree. So you can think about something like quicksort for that. And then the last example is you have a fine-grained data-dependent synchronization. So something like a sparse matrix, or something where you have the sparsity pattern governs the pattern of data dependencies, and so you don't know statically what the pattern is, so you need some kind of runtime mechanism to synchronize that. But you want to make sure that the coding and the runtime mechanism are working together to give you the determinism. And so that's an example where the runtime and the type system work together to provide the guarantee. Yeah.
So one of the examples I recently saw that was you have a very simple partition pattern, but it changes over different phases of the algorithm.
Right.
Can you support that?
I guess I'd have to see more specifically what the example is. So that's, I think in some cases we can, right? So,
for example, for a FFT fast Fourier transform, you would do simple divide and conquer, but in the merge phase, you want to also parallelize that part, and you would have a different partition than for the divide and conquer.
So I think in some cases we can do that. Like I'll show you an example of how we can do, for instance, like quicksort, where you can partition an array dynamically into different chunks, and so we can handle something like that. But there's other cases where the static type system isn't as flexible as we'd like it to be, because in some cases we kind of have to say at object allocation time, okay, this object is parameterized with this region, this other object is parameterized with that region. And if we want to change those regions, currently we can't do that, so that's a limitation. We'd probably need to add more runtime support for that. So I'll talk about some examples that illustrate this.
How about just one where you run columns in one iteration or one section of the code and rows?
That we could probably do. Yeah. Right. Because like in that case, we could probably partition it into rows and columns, and then you just say, okay, you could just specify columns, rows. The difficulties come in where you want to just, you're doing one thing and you just want to do some totally different thing. Okay, but so the point of this slide is just that we've developed some novel patterns. We looked at some codes. We saw, okay, we want to do some things with these regions and effects, and we said, okay, in order to express these common patterns, we need to develop some new techniques. So we've done that for some of the patterns. All right, so the first example, so now I'm going to just sort of go through each of these four things in order. So the first idea here is updating objects through an array, and I contend that the key property in doing this kind of update is what I will call linearity of references. So this is related to the concept of linear types, but it's different, so it shouldn't be confused with that concept. And the reason why I call it linearity is just because if you look at the data structure itself has a linearity property where each object is only pointed to by one reference in the data structure. But there could be arbitrary other objects and local variables and so forth pointing to these objects. So it's not some sort of global linearity requirement like you would get in a linear type system, but it's a linearity requirement when you just kind of look into the data structure. And I contend that that's the property that you want if you're going to do this kind of update in parallel, in a straightforward way. Otherwise, you'd need, to do something like this, you'd need some more complicated synchronization if you wanted to do it deterministically, because you'd have to ensure that, let's say, this one went before that one. But if it's linear, then you can just zoom through and do them all in parallel. So in DPJ, the goal is if you have a linear data structure, you want to express that linearity requirement so that when you do the parallel traversal and update, the compiler will say, okay, that's fine. And the way we do that is we have a novel array type where we leverage these things called region parameters. They're a lot like Java generic parameters. It's just parametric polymorphism. So we have a class C parameterized with some parameter P. So we just extend the type parameters that you get in Java with these region parameters. And then we can say something like cell I of an array, if it's one of these special linear arrays, then cell I can have type C parameterized with region I. And so each cell of the array is actually going to get a different type. And then we can use that typing to enforce that I is only ever assigned to I. So you can't, for instance, assign, I plus K to I. And then that enforces the linearity requirement. So to look at a simple code example, here I've written a class parameterized with P, and I have some update function that's doing some update to the object that I don't specify. But what's important is that it writes P. So here, see, I've declared the effect in terms of the parameter. So when this class is instantiated with some region, then the afferent effect of invoking the update on the instantiated class is writes whatever that region is. You just do the substitution to get the effect. Okay, so then, and then here's a pictorially sort of what it looks like. I want to have an array of these C's, and I want the 0th one to point to a C with a 0 bound to it, and the 4th one with a 4, and so forth. Okay, yeah?
parameterize a class or a region, does that mean that all fields of the class of an allocated instance are allocated in that region? Or is it a pure formal parameter that you use however you want?
Okay, so not necessarily. So just going quickly back to this example. So remember here, like I could say, field F1 is in R1 and field F2 is in R2. So when I declare a parameter like that, it just becomes another region name that I can use. So I could say, I could say in F1 and P. So I can just.
So in the array example, it happens to be a property of the code that it allocates the A sub I in region sub I.
Yeah, I mean that's right. So that's one way. So I didn't specify, exactly what this update is. But one thing that could be going on here is you could have some field like X that's in X in P, and then update could write to that field, and then it would write P. Or you could have a whole bunch of fields all declared in P, and they could all be updated, and that would also be covered by this effect, right? Okay. Okay. So then, in the simple example of the parallel traversal and update, there's basically three things you need to do, right, for the pattern. So the first one is you need to declare an array, and it's going to have some type. And the type is going to tell you that the array has this linearity property. And the linearity property is going to be preserved by all uses of the array so that when you finally get to the update, it works. Okay. So the type annotation we have here is we just put an underscore. So this is somewhat preliminary. We're still sort of hashing over exactly what the syntax should be, but this seems to be one reasonable way to do it. That you just need to put something in there to indicate this property that says that when this array is instantiated and you take the ith element out of it, the type you get out of it is C parameterized with I. Okay, so we put an underscore to indicate that. All right, so that declares a linear array. Then you want to create and initialize. Well, so I haven't actually shown the array creation, right? But you would just say new to actually create the array. And then you want to initialize the array. So here I have a for each that just does a stride 1 traversal from 0 to the length of array a minus 1. And then I can just zoom over that and create a new C parameterized with I on the ith iteration and put it in. And the compiler can just do this very simple symbolic comparison and say, okay, yeah, whatever I is, this I is going to be equal to this I, so the typing works out okay. And we can do more complicated examples, but it would just be sort of limited by the the symbolic comparison capabilities. But what we found is that in a lot of cases, you just have, simple comparisons like this. So it's just mostly like a bookkeeping thing. It's just sort of documenting that you're following this pattern correctly. And then the last thing you want to do is go, again, zoom over the elements and update them in parallel. And in this case, as I indicated before, the compiler can infer from this use and this declaration over here and the static type of A, right? So you put all that together, and you get that on the ith iteration, the effect of this method call is writes region I. And since the traversal here is at stride 1, and you're just going in order, over the i's, on a different iteration, you get a different I, so it works. Okay, so it's sort of putting together all the pieces to prove the determinism in that case.
So how complicated can the formula on the A sub I be? Can I do like 2 times I plus 5?
Yeah, you can do an arbitrary thing. It's just that, if you really push the bounds of the symbol comparison, then the compiler might not be able to prove that they're equal. And then it would just complain and say, I can't prove that these are equal.
So it can handle sort of simple linear functions. But things like mod or divide and things like that would come back with a false.
Well, it would have all the problems. I mean, we haven't really investigated this specifically, but it would have whatever the problems are, and for dependence analysis that you get into. Yeah, so I would assume that affine functions, like ax plus b would probably do just fine, and then other things, be harder. So yeah. Okay, so then just to go into a little more depth. So when I presented this material at Illinois last month, there was a question about sort of what happens when you have multiple pointers pointing into an array. So this is an example where I've got two. Where I've got two reference variables, right, that are pointing into the same linear array. So I can do something like, it's okay to go over the array and update it, and then I can go over the array and update it again. And that's fine, like if I just did that sequentially. But then if I want to do those two things in parallel, that should be illegal, right, because the reference is alias. Okay, and the way I know this is because if I look at the effect of this entire statement, I know that it's writing, regions I. That's what I know about it. And I also know that this statement is writing regions I, and I can't distinguish the regions I that those statements are writing, so I say that's not allowed. So the compiler says, not allowed. But if you go to a different example where you have two different references pointing to two different arrays, then you can distinguish them. And the way you do it is so there's this extra information we allow here where we can actually parameterize the whole array. So it's kind of like a class region parameter. You can just think of the array as like a special kind of class. And so there can be a parameter for the whole array. And then this one can say, well, okay, each element is in region I, but the whole array is also in R1. And then so we use this nested syntax here. So in a little bit, I'll explain more how this nesting works, right? But the basic idea is just that we can, within an array, we can distinguish like 0 from 4. And within this array, we can distinguish 0 from 4. But we can also distinguish this whole array from that whole array because this one is R1 and that one's R2. And then I can say, all right, it's legal to do that again, and it's also legal to do the cobegin. Yeah?
So I think you're going into more and more specialist types. The question is, if you go like 2 slides back.
Yeah. Here?
The question is, how do I get the C of I? It seems like I would be a little bit constrained in creating that in a manner that's reusable across multiple loops or uses, right? Because I just want to call a function that gives me a C.
Right.
In most cases, but I need a function that gives me a C of I.
Right. So what you have to do in order to, it's kind of like dependent types, right? So in order to do that, you have to somehow pass the I in.
Yeah.
And then get the I back out.
Right.
Yeah. So, or you have to pass in enough, you'd have to pass in something and then get back some function of it such that you could prove the equality. You can use some symbolic comparison to prove that it's equal, right?
Okay, and if we go to the next example, I would need to pass in both the R and the I, right?
In this case?
Yeah.
Sorry. Yeah, well, so in this case, the R you would probably be able to get from the type. Yeah, but you'd have to pass. So R in that case would either be some global name that you could just refer to, or it could be something that's bound to a class parameter or a method region parameter. So it's kind of like Java generics, right? You can name the type, or it can be parametric. If you want it to be scoped, or you want to reuse it with different names, then you create a parameter and pass it in. So basically, the I index thing works an awful lot like these names. It's basically the same kind of thing, except that you have this extra wrinkle because you have, it's a runtime value, so you don't have as much information about what it actually is. It's not just a name; it's a value. So. Okay. All right, so then to conclude the linear arrays example, so there's a couple of extensions that we're thinking about to sort of address some limitations here, right? So the first one is that, this works well for some common simple cases of updating parallel arrays, but in general, we're going to need more flexibility. So for instance, if you want to take an array and permute its elements, we can't really do that, right? And still maintain linearity because we're requiring that we only ever assign, if an object is created with region I, then it's only ever assigned into the ith position of any array, basically. So one way we could do this is we could just maintain some metadata in the array and just check that the same element isn't inserted twice. And then if it is inserted twice, we can complain, right? So the user could say, I want this array to be linear. I think it's linear. And then at runtime, you can just check and see whether it's linear or not. So that provides more flexibility, but the guarantee is weaker because if it turns out to be not linear, then you have to stop. Yes?
Did you think about going towards true linearity, like a linear type system?
Thought about it. And I've played around with that a little. It's just that introduces a whole lot of other restrictions. So I do have some ideas on things to do with linear types. But that's sort of more explorational work. Yeah. So.
The difficult part there is how to introduce something that isn't as restrictive as full-blown linear types, and allows you to express a wide range of value more than what we
Yeah, I think so. Linear types are nice because, for instance, linear types wouldn't have this problem, right? You could permute things, and since you only have one reference outstanding, it's no problem there. But then aliasing becomes really, really hard. I found that when you start programming with linear types, then a lot of times you end up programming in a very functional style, which is okay, but it's just not the way people tend to program in Java. You'd have to pass something in, and then you always have to give it back. It's like you send it in and you give it back. And it means you end up having to rewrite a lot of common patterns. So it's just a trade-off. Yeah. Okay, so another important extension to this is to extend it to more general collections, right? So right now we only do basically indexed dense arrays, right? So dense index structures. We'd like to do sparse structures, sets, maps, things like that, things that aren't necessarily indexed. So it's just a collection, it's a collection of things, right? With a little less structure. So one way we could do that is we could extend our for each construct so that you're just iterating over the elements of some collection like a set. And then if we can guarantee that, or if we know somehow that each element of the structure is unique, like it's a set. So sets are supposed to have this property, of course, modulo the issues that come up. Object comparison is always a tricky thing, like because it depends on the semantic definition of when two objects are the same. But assuming that you only have one of each object in the set, then you should be able to do this, and you should be able to just extend the idea so that this underscore thing becomes an implicit parameter that's kind of bound to the iterator, right, instead of being bound to like a numerical index. So we think we can do that. All right, so that's all I had on linear arrays. So now I want to go on to this nesting concept, which is sort of the second point that I was talking about in the parallel patterns. Okay, so I showed this a little bit in the array example. So the idea is that we have a tree of regions, and the region nesting forms a tree. And this is an example of how we could do it, right? So we have a root region, and then under root we can have something like root colon R1 and root colon R2, and then under root colon R1 we can have more nesting, with a 0 and a 1, and similarly over here. And we can just sort of combine that. It's very flexible that you can just combine these names in arbitrary ways and create these things that we call region path lists or RPLs. So the idea is, something like root colon A colon B is a region path list because it kind of denotes a path in the tree. And when you see something like root colon A colon B, you know syntactically that that's nested under root colon A. So the nesting is sort of a syntactic comparison. And the importance of this is that, as we've already seen in the array example, you need to be able to group regions, right? So you need to be able to say, like, I want to distinguish this 0 from this 1 here and that 0 from that other one, but I also want to be able to distinguish like these two from these other two, right? So it just provides that kind of flexibility. Okay, so as an example, you can make a tree data type. So you can, not surprisingly, you can use the tree, region trees, to make an actual tree. So here's how you do it. You declare a tree object that has one region parameter P. You can declare regions L and R. You have some data. You can put that in the P, which is the parameter of the class. And then you do this tricky thing with types, right? So you say the left reference is going to have two attributes. It's going to be in region P colon L. So this says, the region that's nested under P that's named by starting at P and then L. Okay? And then you're also going to say that the type of that left is a tree that's bound to P colon L. And similarly for the right one. And then at runtime, that might expand out to something like this, right? So to see how this expands out, you just start plugging in for the parameters. So you might instantiate a tree whose root is has its parameter bound to the root region. And then you would just plug root in for P and all these things. And then, you say, okay, the data is in region root. The left thing is in region root colon L. And the right thing is in region root colon R. And also, you know that the type of left is tree with parameter root colon L. And so that's indicated by this arrow here, right? And then, so so that's a static restriction on the assignment you can do. So this has this property that, okay, now root colon L is bound to the P, and again, you substitute in, and same thing for the right one. And then because of this nesting property, and because L and R are always different, then you have a tree. Okay, yes?
I could also just choose to place left and right the fields just in P, right?
Yeah, you can do that.
Right?
Yeah, you could do that.
That I give up the ability to work on them in parallel.
Right.
Okay. But I could still traverse the subtrees.
Absolutely.
Okay.
Yeah, and another thing you can do to make it a little, if you need a little more fine-grained distinction, is you could declare another region that's the region of the links. So you could put all the links in a region, and then the effects can say, I'm reading the links, but I'm updating the data regions in parallel. You can do things like that, yeah. Okay, so that gets to this, which is a very simple example of how you can specify tree-like effects. So this is the same tree up here that I showed before with a little picture of the actual tree And then the boxes show like the groupings, right? So this shows how at the root, like sort of looking at things from the perspective of the root, I can have the left subtree and the right subtree, and I know that they're disjoint. Like, nothing ever points across, at least nothing that I'm following. So that's one thing about this system is you can have arbitrary pointers going across these regions, right? It's just that you have to declare what you're doing. So if you ever follow one of those pointers across, you have to say you're doing that, and then you lose the tree structure of the parallelism. But if you're not ever doing that, then you can specify that, and then the traversal works fine. So in this example, I have an increment method that's just going to zoom down the tree and update in parallel, just increment all the data in all the nodes, right? And I can do this because I can do the left subtree independently of the right subtree, and then similarly with the recursion. So I have, the way I do that is I can infer when I do left dot increment that I'm writing p colon l colon star, and I can infer when I do the right dot increment that I'm writing p colon r colon star, right? And I get this from two things. It's the type of the dispatch object left, right? So here it's like p colon l, that's its type. And then I plug that into the declared effect of the method, which is here. It's recursive, right? But the method is declared with the rights p colon star. So when I plug p colon l in for p and p colon star, I get p colon l colon star. All right, and then when I do that, it's an easy matter to infer that p colon l colon star and p colon r colon star are disjoint for any binding to p, right? So that's the key point. Statically, I don't know ever what exactly that p is, but I know whatever it is, I can make this inference and it's sound. Okay. All right, so that's all I had on that, the nesting and the nested effects. So next, I can go on to the divide and conquer operations. So this is a similar kind of concept, but you're just doing it on a flat array instead of a tree. So to do this, we introduce a couple of language features. So we have something called a subarray, which is pointing into a subrange of an array. So it's basically a view. So this is a concept that Java uses in other contexts where you have an array and then you have another object that points to the original object, but it just looks like a contiguous subset, right? So and then it'll compute the offsets so that you can just index into the subset, and then it'll compute the proper index into the underlying thing. And then we also have a partition, which is a collection of disjoint subarrays. So you can take an array, you can chop it into two disjoint subarrays, and make a partition out of that. And then the partition object kind of knows the disjointness property and can use that to infer the correctness of the updates. And then in the type system, we have that each subarray in a partition is going to be in a distinct region. And then we can use recursion to make this flat array into a tree of regions. And so this aspect of the type system is kind of like object ownership. So we're basically making a tree of objects instead of a tree of static names. Okay, so very quickly, code example. Here we're using a method parameter, which is kind of like a class region parameter, but it's just on the method. And Java has something very similar for generics. So the method is going to take one of these special arrays that is parameterized by a region, and it's going to say it writes under that region. Then it's going to do some bookkeeping stuff for the quicksort algorithm. And this one is actually going to have an effect that writes, this method is actually writing the array because it's shuffling the array around. Then I'm going to create a partition out of this array. So I'm going to have two segments. And then I say open here just to indicate that I'm not including the actual index position in the partitioning, right? So I have this left one and this right one, not including the pivot. And now I can traverse them in parallel and update them. And the type system is going to tell me that that works. So, and then we have this type where we can actually use a variable as kind of like an basically use a local variable as an RPL. And that tells you that you're using the object's references as the tree. And that's what allows you to do this dynamic partitioning. Okay. All right, so, and then the last thing I wanted to talk about briefly, so, oh yeah, sure, go ahead.
The commenter type of sex I is DPJ array int.
Yeah.
Sex colon I.
Yeah.
So what does sex there mean as a name of a region?
Right. Okay. So that's what I was mentioning. That so what you can do is you can make a local variable here, segs, right, and you can assign a partition to it, and then you can use that local variable as it's as a region name. Yeah. And so it works kind of like, I don't know if you're familiar with object ownership, but it works kind of like that. And you're basically saying that the object reference, right, that lives in that variable is the region. Okay.
Are there other restrictions that you want to say? So, like, you can't copy its.
Yeah, so actually one restriction that we do have, which, all right, so this is a little misleading because I should have put this restriction in here, is that we require it to be final. So this should say final. Just because if you start reading and writing, if you start writing a different reference in and then you have different uses, you could do data flow analysis, to prove that things are the same or not the same or whatever. But just to make it simpler, we just say, well, if you're going to use one of these variables as a region, then you want to make it final so you know that every use is always basically referring to the same thing, right?
Pass it to a method and have the type. If the called method used the formal parameter name in this way, could you have it be the same type as in the caller?
Yeah, that's an interesting question. So we can definitely do that in the case where, so I think that's basically what we're doing here, right? Because, well, no, actually, so here we're just doing it with a method region parameter. So I think you definitely can get something like that in the case where you substitute for this. I don't know, I'll have to think about that a little more. I mean, if you're interested, we can go through some examples. And so, because you definitely do some variable substitution, when you're at the point of a method call. That definitely happens. Okay, so the last point I wanted to talk about on the parallel patterns is this fine-grained synchronization. So this is very preliminary work. I mean, right now, this is sort of an idea that we have for how to handle this. And we're looking into how this might work for something like a sparse Cholesky factorization code. But just to illustrate the point, I have a much simpler example here. So the idea is we have this region that we can declare with the sync keyword, and then that's actually going to create a runtime construct that's used for synchronization. So all the regions that I showed before were erased. They're all just static things that the compiler would check and then get rid of, right? But this is something that actually hangs around at runtime because in this example, you need some synchronization to do this deterministically, right? You want to enforce that this access, the access through 1 to C goes before the access to 5. So to do this, have class C with some data that's in this sync region. I have some work method that's doing an update, but now I'm saying this.r. So because it's a sync region, it's at object granularity. So I can say this.r. And then I can have a parallel work that takes an array. And now I'm using a task spawning style here, which is a little different than what I showed before. So I'm running over the array sequentially and then spawning some work on each of the elements. And what's going to happen here is the runtime is going to make this work. Okay, so the key idea is that there's a queue associated with each of these sync regions. And so in this case, you get one sync region for each object you create. So each object has a little queue associated with it. And when you do one of these spawns, the spawn is actually going to put the declared effect. So it's going to infer what the effect of this spawn statement is. And in this case, it's writes this.r. So it's writes a of i.r. But at runtime, that a of i is going to get resolved to a reference. And it's going to follow that reference, and it's going to find a queue, and it's going to put writes reference.r onto that, or writes r onto that queue, and then continue. And similarly, when it gets to 3, it's going to do the same thing. But when it gets to 5, it's going to put that effect on Q1, but it's going to wait until the first one is done before it can proceed. And that's what guarantees. So basically, the sequential order of issuing the spawns together with the ordering property of the queue is going to guarantee that its execution is deterministic. And it's also deadlock free. Yeah.
So you have to have a queue for every element of that.
Yeah.
It's a 2-pass thing, essentially. So first pass, you queue all the
elements, exactly.
Okay.
And right, so there are a lot of issues with making this efficient. I mean, obviously, you don't want to do this on every element, right? You want to have some sort of partitioning for efficiency purposes. And yeah.
To be more clear, I mean, if you're saying Q1 and Q3, if the two C's were C sub A and C sub B, really the right way to think of it is C sub A dot Q and C sub B dot Q. It's not associated with the array indexes. It's associated with the.
It's associated with the object, right?
Okay.
And the objects get resolved at runtime, so that it sort of saves the compiler from having to do some very complicated alias analysis to prove. Now, you might be able to do some alias analysis to optimize things. Like you might be able to say, okay, well, since I'm already waiting on this queue, I don't actually need to wait on this other queue or something like that. But this is sort of the basic mechanism: is you just leave it. You leave the object reference distinctions to the runtime.
This type of transformation is very common in parallel algorithms, like doing histogram calculation.
Yeah.
So
Right.
just really general.
Or for sparse matrix kinds of algorithms where the sparsity pattern is unknown until runtime. So the actual data dependencies become dependent on the zero, on the sparsity pattern of the array.
Right.
And that's exactly what happens in sparse Cholesky. Column up, if you do a column motion, the column updates depend on the sparsity pattern. So which ones are parallel depend on the sparsity?
Yeah, so tentatively, like the next thing I'm going to be working on for my thesis is like looking at how to apply this idea to sparse Cholesky. That's kind of what I'm doing right now.
And each of these queues can obviously be processed in parallel.
Right.
You don't actually have to fill all the queues up, right? You can start as soon as you get the first guy.
Yeah,
Because
yeah,
you're going
yeah,
through that
yeah.
in order.
Right, basically at the point where you put something on the queue and you see that you're at the head, if there's nothing else there, then you...
So you can have one thread just put things on the queue and all the 99 other guys taking things off the queues. Or whatever.
Okay, so I can talk very, very briefly about the implementation we've done. So we've developed a preliminary compiler that does a DPJ to Java translation. It extends the Java C compiler from Sun, and it uses the fork join task framework, which is a library written by Doug Lee and others, I guess, that's supposed to be part of Java 7, but it's not part of Java yet, just yet. It uses a work stealing task scheduler, so it's similar to Silk. And we have a few benchmarks. So we actually have coded up some other benchmarks, but these are the ones that we use for the performance numbers. So we have a standard merge sort implementation, a couple of programs from Java Grande benchmark suite, a Monte Carlo simulation, and an encryption algorithm. And we have the force computation, which is the most compute-intensive part of the Barnes-Hut n-body simulations, used a lot in astrophysics. And we have a collision tree algorithm from a graphics engine. And to do the experiments, we used a 4x6 core x86 machine with 2 gig memory per core for all but the graphics engine, which needed some more heavy-duty graphics stuff. So we used an Apple Mac Pro for that. But we're actually working on trying to get this to run on the Dell so that we can have uniform numbers for all the benchmarks. Okay, so I apologize if this graph is a little hard to read. Hopefully you can see what's going on. But you can see that the numbers are kind of all over the place, right? So basically we have two applications that are doing quite well. That's the IDEA and the merge sort. We have one application that's doing okay and not great. That's Monte Carlo. The thing is that the Monte Carlo just has some scalability limitations built into it that are even in the Java thread implementation. So we're equaling or exceeding the performance of the Java threads with that one. So this, in some sense, it's not our fault, right, that this is not scaling. So we're pretty happy with those three. Barnes-Hut right now is very, very disappointing. It's just not scaling at all. And there's actually a couple other students at U of I who have been working very, very hard on trying to figure out why this isn't scaling. But our best understanding at this point in time is that it has something to do with the actual Java, that it's the JVM. That basically, there's a student who actually wrote this out in Java threads, and it still is not scaling. So it seems to have nothing to do with anything that we're doing in DPJ. It's just a performance issue that we need to solve in order to make progress with this particular benchmark. And then for the collision tree, it's scaling okay, but then it seems to flatten off. It's kind of hard to tell because we're only running it on 7 cores there. Okay, so this is basically what I just said. We're still working on Barnes-Hut. But we did get good performance for at least a couple of them. Really for 3, we got good performance, so that's encouraging. Okay, so now going back to the research goals. So the next issue is how to encapsulate the local nondeterminism. And so for that, there's basically two kinds of encapsulation. So one is something like a sum reduce, where this is what I said before, right? Where you just have a deterministic operation, and there's some nondeterminism going on inside that operation, but the client really doesn't care at all what's going on in there. Then the more complicated example is if you have something like a reduction or a commutative container operation where there's some interaction between the encapsulated code and the client code. So maybe the client is providing some operation that's going to be used for the reduction, right? And then maybe the library is going to require that be an associative operation, or maybe you have a set that has a commutative insert method, but the parallel client code, in order to take advantage of that, has to know which ones commute and which ones don't, and the compiler has to know that in order to check things. Okay. So on the example of commutative operations, so we actually have an idea here on what to do, and I've actually worked this out. So this is part of our type system. So we add a commutativity annotation on methods that commute, right? And this is something that a library programmer would provide. So we anticipate that a skilled programmer would write some sort of library that would have a commutative method, and then there'd be some sort of extensive testing to make sure that the commutativity is correctly implemented, and then that fact would be recorded with an annotation. So this ordinarily is not something that Joe Average client is probably going to be writing. But then what's going to happen is on the client side, when you invoke one of these methods, the compiler can see the commutativity annotation, and the compiler is also going to record what we call an invocation effect. So it's kind of extending the concept of effects from reads this, writes that, to does this method with such and such effects. So you've recorded both what you're reading and writing on the heap, but also which method calls generated which effects, so that when you get something like this, where you're in parallel doing a bunch of set adds, the compiler can say, okay, the effect on iteration I is, add with a write to whatever region the set is in, and the regions are all the same, and those are all writes, but because the set add is declared with the commute, that's green, that's okay. But then over here, if we did an add and a find in parallel, that could be non-deterministic, so that's not allowed. And another way we could get it green clearly is if we did a set add on one set and a set add on a different set. We could just use the mechanism I showed before to just distinguish those two sets, right? But where you're doing it on the same set, you need this annotation. All right, and then so moving on to explicit nondeterminism. So now I'm getting into the part of the work that's a little more preliminary. So this is more in the nature of ideas we have for things to do, but we haven't worked out in as much detail how to actually do it. So our idea here is that we recognize that some algorithms are non-deterministic. Examples include branch and bound search, Delaunay mesh refinement, which is, I believe this is one of the stamp benchmarks, and it's gotten some attention in the literature. Graph clustering is another example. So basically what's going on here is that you have a problem. It's a compute problem, so you're giving an input and producing an output, but you might want to tolerate some non-determinism. You may want to say, okay, well, any one of a class of answers is okay, because if you restrict to one particular answer, you're just limiting yourself too much, and you will lose performance, and you might seriously lose performance. So you really don't want to do that. So you're giving up some determinism to get performance. So in this case, usually it's one or more phases of a larger program, and to support this, you need some kind of transactional or other non-deterministic semantics. Okay. So we have some requirements. We eventually want to allow this kind of thing, but with some limitations, right? So we want it to be explicit, first of all. This is really important because we want the programmer to say that they want it. And if they don't say that, then they don't get it. We want it to be data race free so that you don't get kind of low-level interactions that are hard to reason about. And we also want it to be confined in the sense that we'd like to be able to look at the structure of the program, and also together with the semantics of the constructs we provide, we want to ensure that there's no interference, or at least unwanted interference, between the deterministic part and the non-deterministic part. So some examples here. I have this for each SD construct. So SD here means schedule dependent, and it's just extending the for each construct to relax the requirement that the iterations be non-interfering so that everything is deterministic. So here, for this one, interference is allowed. You can have conflicting reads and writes on the different iterations. But if you do that, there's going to be some kind of atomicity enforcement. It would probably be in the nature of hardware, software, transactional memory kind of thing. But what's important here is that even though we've introduced some non-determinism here, right, this part's deterministic, at least when you look locally at what's happening in this loop. So if there's some data that's being produced here that's used in the next block, that might introduce some non-determinism, right? Because this could produce a non-deterministic answer, but you could still look at this section of code and reason deterministically about it. Okay, and we just think that's very important. And similarly over here, you can put the for each inside the for each SD, and even though there's some non-determinism going on in this whole block, inside the block, you know that, let's say, on some iteration of this for each SD, you're going to do a for each, and inside that for each, you're going to get deterministic results. So again, you can reason locally about the determinism, even though you've introduced non-determinism. And so we just need to work out in more detail, how these mechanisms are actually going to work and be implemented and so forth. But this is sort of our ideas at this point. Okay, and then the fourth point that I'd like to touch on briefly is this concept of making things more usable, helping programmers write the regions, figuring out how to annotate things, and also maybe where the code needs to be revised in order to expose parallelism and so forth. And in particular, how to take legacy code and port it to a language that uses these concepts. So our sort of broad vision for this kind of porting environment is that we want to leverage parallelizing compiler technology that's been well studied and well developed. It hasn't really caught on in the mainstream, but we believe that's because of some limitations when you apply it. If you want to do things fully automatically, it introduces some severe limitations that hopefully we can overcome by making it more interactive, right? So that allows programmers to verify choices, right? So the compiler can say, well, I think this is going to work, and the programmer can look at it and see whether that's true. And we believe that can hopefully circumvent the fundamental weakness of auto-parallelization, which is basically that auto-parallelizing compilers have to be very, very conservative because anything they do has to be guaranteed correct. Also, the types of inference that or analysis that the compiler is going to be doing is going to be a recommendation. So it's going to be interactive in the sense that the programmer can see what's going on and not just some black box transformation that just, not something like, okay, I vectorized this loop or I didn't vectorize this loop. It's going to be sort of more, hopefully provide more information about, what went wrong or where things might need to be changed to make it work, things like that. So hopefully there's going to be high-level changes and also allow programmers to understand what's going on so that they can kind of do a feedback loop where they'll get some results from the compiler and then think about some things to change and then feed it to the compiler again and so forth. And also we think it's really important to produce readable, maintainable code. So you want to preserve comments, macros, things like that so that you're not just generating unreadable code, because that would sort of defeat the purpose of having this interactive loop. Okay, so for DPJ, so first of all, this vision is a very broad vision for a porting environment for a deterministic language, right? So it's not even specific to DPJ. It's very, very high level. But to start working on this, we're starting with DPJ as a target, and we're starting with something very basic, which is effect inference. So you might have noticed that in the system I described before, it's somewhat heavy on the annotations in the sense that you have to write everything out, even method, effect summaries, and all that. And we believe that's the right way to start because that's how you can hammer out the ideas and make sure it works, improve its sound, and all that. But then sort of once you've taken that first step, then I think you really want to work on making it easier for the programmer. And one way to do this that we believe is going to be fairly straightforward is to infer the method effect summaries, at least in a lot of cases, right? So the programmer can declare the regions and the region parameters, but then the compiler can look at a block of statements and just, record all the effects going on and then insert the summary into method. So it should make the language more usable. Okay. And the next step after that is to actually infer the regions. And that's a much harder problem because really what you're trying to do there is look at the parallel access patterns and say, okay, for example, this part of an object is being accessed in parallel with that other part of an object, so therefore I've got to put those two parts of the objects in different regions, right? And that's something where, in order to do that reasonably well, it's probably going to require a fair amount of interaction between the compiler and the programmer, right? Because the programmer is going to have to bring his or her knowledge and insight to the problem. You can't just throw that at a compiler and expect it to work well. But hopefully, if we make it interactive, then it should be tractable, at least in important common cases. Okay, so in conclusion, I've presented an overview of this project that we're doing, DPJ, Deterministic Parallel Java. It's an object-oriented imperative language where the compiler is guaranteeing determinism with some runtime support. Presented an overview of the research agenda, so that mainly includes expressing determinism, expressing controlled non-determinism, and dealing with usability issues and porting issues. And I showed some preliminary results, including novel features of the type system, very preliminary performance results, and some ideas for extending the language that we're working on. And so that's what I have, so I can take any more questions. Okay, yeah? Go ahead.
Actually, I have a very basic question. Like, you're talking about deterministic, so what kind of property you're looking for will allow you to derive the deterministic conclusion? It sounds like you're looking for the property that's the updates to the different region, which equal to deterministic, if that's...
Yeah, well, right. So I guess how I would summarize the property is, so there's basically two properties. One is that you have like disjoint concurrency, right? So like if you're doing a for each, then the reads and writes, the conflicting reads and writes are disjoint, right? So basically for any pair of memory accesses happening in parallel, either the accesses commute or they're disjoint, right? And then the other property would be, for this fine-grained synchronization thing, you might allow some interference like that, but you have some synchronization mechanism that just makes sure that the write always happens before the read that needs to access the write, things like that. That's how I would summarize it. Property, yeah. Yeah, that's a very good question. So right now we are just using the ostrich algorithm. Or just ignore it, right? No, but so basically, I believe that I/O can be done in a similar way, right? I mean, you could have I/O regions just like you can have memory regions. I guess like the simplest way to handle I/O and get safety, right, is just to say, well, anytime I do an I/O operation inside some parallel region, right? That could be potentially conflicting, but that's very limiting. For instance, like you wouldn't be able to do parallel I/O. That might be okay if you don't have a parallel I/O system and you don't really want to be doing parallel I/O anyway. And so we think that for a lot of these compute-intensive applications, probably the model is read a bunch of stuff into memory, compute on it, and then write it back out, and we can handle it just fine. If we needed to do some sort of parallel I/O stuff, then I think the model could be extended that way. Yeah. So go ahead.
So Cyclone is a language that uses at least the name regions for
a
similar concept.
Yeah.
And they try to use it largely to prove the safety of memory deallocation.
Right.
Example.
Yeah.
I wondered if you thought about whether the ideas are similar enough that you could get some of the things they get out of their region system.
Yeah, I think you definitely could. Yeah. Right. So region-based memory management is closely related to region-based non-interference stuff, which is what I've been talking about. I just think there's some differences because I think the use patterns are different, right? So, I think it would be useful to look at something like Cyclone and say, okay, if we wanted to design a comprehensive language that could do what Cyclone's doing and can do what we're doing, what would that look like? That would definitely be a useful thing to do. And there's definitely some overlap.
So I think one thing that's a little different way to do is inferring regions in their kind of language, I think is a little easier because they have to infer regions purely based on lifetimes of objects. And here we have to analyze sharing patterns between threads. And in addition to that, so for example, for that tree example, in the tree example, we would have to infer that the objects actually are form a tree, which requires shape analysis to be able to do that, and that's quite difficult.
So, oh, okay, yeah, sorry, go ahead.
You talked about non-determinism due to concurrency,
Yeah.
how we handle that.
Right.
But what about non-determinism due to interactions with the runtime system? Do you also require like the operating system to be deterministic?
No.
So how do you handle that?
Yeah, so basically, our thinking on that is that we're going to tolerate whatever kind of non-determinism is sort of already in your sequential programming model. But are you thinking of maybe non-determinism that would come in because of like parallel?
Right. Like let's say you're sending data across a network connection, and then or you're receiving data from a socket, and you break it up into packets, and whichever thread gets scheduled just picks up the packet like a regular one.
Well, I think so. In that case, I guess it depends on what you're doing. I mean, if you're doing some computation that's actually the end result of which is intended to be deterministic, right? Then you would have to encapsulate or sort of insulate that particular non-determinism in some way, right? You'd have to say, okay, I'll get the packets in different order, but at some higher level, the way I compute on them doesn't really matter. The order doesn't really matter. The order in which I receive them doesn't really matter or something. If it's really non-deterministic, then you would explicitly request that kind of non-determinism. So I guess it really just depends on the application, right? So we haven't really looked at, say, like network applications. That's just not something we've studied. So I guess I don't have a really good specific answer for that application, but that's sort of the general way that we go about it. So.
Object hash codes are generally random.
Right.
Do you have any issues where you might want to use those, but that's going to cause non-determinism?
So we haven't run into that particular issue, but my sense is that you could use something like the commutativity annotation that I showed before, right? So the commutativity annotation, that's specifically for data structures, but the way I showed it, right? But you could do something similar. You can have an interface that wraps some little localized non-determinism, like I'm generating a hash code or I'm updating a counter or something, and you could declare that you have a little bit of non-determinism that's tolerable there. I think what I have run into is that defining the semantics of that can be pretty tricky because, like in the case of a set, the set semantics is actually deterministic, even though, let's say, the individual operations going on inside are non-deterministic. In the case of like a hash code or updating a counter or something, you may actually be introducing a little bit of non-determinism at the algorithm level. But I think the right way to handle that, again, is to fall back on this principle that says, well, if you want that kind of non-determinism, then you're allowed to have it, but you have to say it. Right? So you have something that clearly marks, like at this point in the program, I'm introducing a limited amount of non-determinism. And then hopefully you can still reason, because people do this, right? They introduce little bits of non-determinism to their code, and it doesn't interfere too much with your ability to reason about the code. If you have a little hash code or something like that, it's not like a data race can occur anywhere in the program, and I just have no idea what's going on. So, yeah, okay.
So it all depends very much on the correct definition of the regions, like what assigned to which.
Yeah.
So I understand that in some algorithms which are in some sense well structured, it's natural to say that this is not region, this is not region. But it looks like there might be many more other algorithms which don't allow easy definition. So how do you think it is easy for the programmer to find these regions? And is it really easier than just fine-grained logic? It's a simple problem.
Well, that's a really interesting question. Certainly if you put in the regions, then you get better guarantees than you get with fine-grained locking, right? Because if you use fine-grained locking, then you're just totally on your own, right? As far as whether it's correct.
Basically, my question is, if you can put regions logically, you're fine. It's great.
Yeah.
So do you have any feeling about what is proportional algorithms which don't allow this logical putting of regions?
Can I try to answer that? Sure. So I think it's a good question, and it's something we only learn by getting more experience with more programs and especially larger programs. But in practice, if you want to parallelize some code, you have to think about the sharing patterns in the code. And really putting in the region annotations fundamentally involves that, because what the region annotations are trying to do are trying to partition the heap in a way so that the sharing patterns become explicit. And if you understand the sharing patterns in the code enough to parallelize the code, I think intuitively you should be able to put in region annotations that capture that. You might be limited by how fine-grained you can make the regions and then put the effect summaries on the methods to get the parallelism that you want. That part, I think we'll only learn with more experience. But analyzing what the partitioning of the heap should be, how it matches the partitioning of the algorithm, the parallelism in the algorithm, that part I think should follow from understanding the parallelism in the code. That's just something that we have to, that's a hypothesis.
I think it may be similar to log composition, just that you do things in different order, right? So let's say you start with an assumption that I need like a lock for this type of object. So I say, okay, all the methods write this object. That's the effect system. And then I try to do some parallel algorithm on my object, and I see, oh, okay, I actually can't have any parallelism. Then I'm thinking, okay, maybe I need finer grained parallelism, right?
And so you could have that kind of iterative process where you put in regions and you find out that you're not getting enough parallelism and you have to refine them. It could also work the other way, that you put in regions and you find that the program doesn't type check because the regions were actually too fine-grained and you had dependencies that were not captured by the regions. And so you had to make them more close. So you could have an iteration and either behavior could happen. But what's nice is you'll never get incorrect answers, unlike with logs. Here, when you put in regions and then you partition, you write any parallel code, the type checker will tell you if you have illegal code.
Right, and another thing that's better than, I think a little better than log composition hopefully is that, with log composition you get this infamous problem where there's like some locking going on in there and you just don't know what it is. And when you try to you try to treat this encapsulated thing as an encapsulated thing and has locks in it. But here at least the region summaries, so that we believe actually this is one benefit of having all the summaries, is that it tells you what's going on. Right, so you can hopefully reason about it a little better. So he had a question.
So in your examples, you described like the way you get the parallelism through the fork join pattern. So for some other application, like some interactive system, like gaming, or like a server client scenario, the level of concurrency or the amount of concurrency you get, it depends on the user input, or the user interaction or the client request, and the server or the need to respond to this request by forking different threads. In that way, in that scenario, how do you apply the DPJ?
So we've been basically confining our attention to programs that aren't like that, right? That's sort of the simple answer for now. I mean, so that's why I started in the beginning and I said, I'm focusing on these programs that are, like we call them, transformative or sort of non-reactive, so that the model is you put in some input, it does some computation, and it gives you some output. So if there's a lot of interaction with the user, then it's not really that model. But I mean, I think some of these ideas could be extended to apply to that kind of model. It's just that's not what we're working on right now. Okay, yeah, go ahead.
So when you have a class C that has a region parameter, do all classes have this implicitly, or you require?
No. So we could. So that's sort of a language design issue, sort of a usability issue that I've thought about. I've sort of gone back and forth on it. Should everybody have an implicit one or not? I mean, right now you have to declare it explicitly, and if you don't declare anything, you just don't get any parameters. If you declare one or more parameters, then you can instantiate a class with no explicit bindings, kind of like a Java raw type, right? But then in that case, there's just some default, like I think the default is just root : star, so it's just like everything. It's just everything, right? But another choice, I think reasonable choice, would be maybe give everybody an implicit parameter and maybe make the default that every every field is like implicitly in that parameter, right? That, I don't know, that might be a better choice. I don't know. I don't know what the best choice is like from a language design point of view, so I just done it this way because it's kind of the simplest, just to illustrate the type system for now. So yeah, go ahead.
For experiments, for like except the fine-grained locking, you need some runtime support for like linear arrays, those stuff.
Yeah.
What's the runtime overhead compared to the sequential normal Java version?
Well, it depends. So for the fully statically typed linear array, it's 0, right? But and then for this other idea that I have, I don't know because it's just sort of a preliminary idea, right? I mean, there would be some overhead, but hopefully it would be pretty small. I mean, I guess for like the runtime checked linear array, I mean, it would be something like a Bloom filter, so it would be hopefully very low overhead, or be some sort of like bit comparison or something like that. So yeah.
Do you have any feeling for the overhead on the one where you had the two arrays, the indirection for the A array, the queuing of
the
it?
queuing thing? Yeah, I guess I'm a little worried that it's going to be hard to get the overhead of that to be reasonable, but we'll have to see. So I think my strategy on that is going to be, start, like as I said, I'm going to look at sparse Cholesky, start with a good implementation of that, sort of see what they do to get that highly efficient, and then see, how I can try to abstract up from that and hopefully preserve as much of that efficiency as possible, right? So yeah.
So for your speed up,
Yeah.
the speed up over what?
It's over the. I think it was over the. Well, it's over the parallelized code running on. I believe isn't that what we did? Or is,
It's a sequential version.
oh, it's a sequential version. Yeah. Oh yeah. Because we have the compiler.
See some speed ups a little less than one.
Yeah.
And for those benchmarks, you always able to statically infer them. There's no runtime overhead.
Right.
The implemented part of DPJ does not include the sync regions
Yeah.
so far, so there's no.
And do you have any idea what the performance, just the raw performance, the execution time was with respect to for Java threads on that?
For Java threads, so.
Not the speed up, but just the total time.
Oh. Yeah, I don't know off the top of my head.
Sorry, what's the question?
Just.
How's the execution? I mean, you show speed ups, right?
Yeah.
So you said your speed ups were a little bit better maybe than the Java threads, right? Or
Yeah.
comparable to a little bit better, right? But what's the execution time?
For the different programs and.
Yeah, compared to, because Java thread could,
Oh, I see what
10
you're
times
saying,
faster,
yeah.
but have less speed up, right, or something.
Well.
If you're injecting runtime checks, people want to know what's the
Right.
sequential slow.
I think we use the same baseline though for both. I think it's the same.
I think they're identical.
I think they're the same program.
Sequential version is identical.
Should be, yeah.
Yeah, I think the sequential version is identical because we took the Java version and.
So they might not be entirely identical. So it's a good question, but there's nothing. It seems like they should be at least very, very similar, right? It's not like we shouldn't be adding any overhead. Yeah. So.
Okay, any other questions? Well, let's thank our speaker.
Okay. Thank you.